Hello students, welcome to this lecture on the combinational circuit families. So in this particular set of lectures, you will see different combinational circuit families, and instead of the regular CMOS structured circuits, we'll try to adopt different widths, making it asymmetric gates. We will adopt different family of circuits called as the pass transistors or the transmission gate circuits, and then there are more towards that. All right, so let's begin with a simple example. Let's try to understand different techniques of designing a combinatorial circuits or a combinational circuits. So here, this is one such example I've taken where we have where we want the output to be equal to nothing but AB plus CD, where AB and CD are the inputs. So I can have this in the form of a multi-stage design. Multi-stage means the first stage I will have some kind of a gates, and then the output of the first stage will be fed to the second stage. So that is called as a multi-stage design configuration. And here you can see that I have designed it using 3 of the NAND gates, where the 2 NAND gates are in the first stage, and then the second one is in the second stage, or rather the third NAND gate is in the second stage. So y is equal to AB plus CD can also be rewritten as nothing but the NAND operation of AB and getting NANDed with another CD, with the NAND gate of the CD output. So basically we need a NAND gate to produce AB bar and a NAND gate to produce CD bar, and then the NAND gate to produce the output of this and an output of this to get the final output of Y. So in this particular example, I've taken some specifications saying that the input should see a total capacitance of 20. So all the inputs, all the 4 inputs sees a capacitance of 20. That means that the gate size is nothing but 20. And the output I have taken as a 100C, where 1C represents the unit NMOS capacitance. So in the multi-stage design, what we will do is we will follow the linear delay model. So we'll find out or evaluate what is the parasitic, normalized parasitics of this particular NAND gate. So we'll take this particular critical path. So let me rewrite this. So let me make a mark here. So this will be our critical path. So in this particular critical path, I need to find out the normalized parasitics for this particular gate and then this particular gate. And that's what I have written here. The parasitic, normalized parasitic of a 2-input NAND gate is nothing but 2. Normalized parasitic of the next stage 2-input NAND gate is 2. The logical effort is 4 by 3 and then 4 by 3. And if I want to find out the path effort here for this particular path, so it will be nothing but 100 divided by 20 multiplied by 4 by 3 and then 4 by 3. All right, so that turns out to be 8.88. For a two-stage design, our path effort is 8.88. So the single stage should see the single stage effort delay turns out to be 8.88, and then the square root of that, which will be nothing but 2.98. And then from 2.98, I should be able to find out what should be the size of this particular gate, because I think the first stage NAND gates, we anyways know what is the size here because it is given as 20 and 20. So we need to find out what is the size of this particular gate, and then that is possible if I can evaluate from the F cap, which is nothing but the best individual stage effort. I can equate it to 4 by 3 100 by X. Right, so from here I should be able to find out what is the X value. So I should be able to evaluate the X value. That's what I have that's what I have mentioned here, which is nothing but 2.98 will give me X is equal to 44.72. The overall delay, if I have the size of 44.72 here, which is nothing but the best size for a 2-stage design. So the minimum delay turns out to be the summation of all the parasitics plus 2 stages, so 2 multiplied by the individual stage efforts, which is nothing but F cap. So the number of the total parasitics turns out for this particular path will be nothing but the 2 parasitics coming from this first stage 2-input NAND gate, and then 2 parasitics coming from the second stage 2-input NAND gate. So the total of parasitics will be 4 here, and the total the effort delay will be nothing but two stages, so 2 twice multiplied by 2 multiplied by the individual f cap. So it turns out to be the overall delay is 9.96 for a multi-stage design. Now we can actually redesign the circuit y is equal to AB plus CD. We can redesign it as a compound gate. That means that it will be a single stage, and we will make conduction topology, wherein we will have a set of NMOS transistors either in series and parallel, and the replica of that, the mirror replica of that, the conduction complement replica of that will go into the PMOS side. So, but that will be a single stage circuit. Right, so just to complete our multi-stage design, this X is what we had calculated, turns out to be 44.72, and then in the first stage we had a size of 20. There were two such 2-input NAND gates, right? So I'm going to write it as two numbers here representing the 2-input NAND gate of the size of the gate size of 20, forming the first stage, and here we have one number because in the second stage we had only one 2-input NAND gates with a 44.72 size. And if I want to find out what is the width of the NMOS and PMOS transistors, we know that for a 2-input NAND gate, we should have a size of 2 and 2, and 2 in the PMOS side and then 2 in the NMOS side. So we'll make 4 parts of this. 2 parts will go to the PMOS side and then 2 parts will go to the NMOS side. So that's how we have done. So equal parts 22.36 and 22.36 will go into the respective NMOS and PMOS transistors. For this particular, the first stage gate size of 20, we know that the PMOS and NMOS should get the equal parts. So 10 of this will go to the PMOS, and then 10 of that will go to the NMOS. What we have is in the first stage of the circuit, we should have one more set of the 4 transistors, right? Because there are 2 in numbers. In the second stage, we have only one such 2-input NAND gate. Right, so if I want to find out the total area, what we are trying to find out is what is the total width. So the total width on the NMOS side, is nothing but 10 plus 10, and this is kind of we have 2 such numbers. So I will have 10 plus 10, 20 multiplied by 2, which is 40 on the NMOS side. So the width on the NMOS side is 40 here. And on the NMOS side, the width here of this particular second stage 2-input NAND gate turns out to be nothing but 22.36 multiplied by 2. All right. So the total width on the NMOS side turns out to be 22.36 multiplied by 2 and then plus 40, which is nothing but 10 into 4. 84.72 is the total size on the NMOS side. And then similarly, we can find out the total width on the PMOS side, which is nothing but 22.36 multiplied by 2 and then 10 multiplied by 4, so 84.72. All right, so hope this is clear. So what we had identified is the delay somewhere around 9 point something, and then the overall width on the NMOS and PMOS side is 84.72. So let me just go to the next one. What we need is a compound design. So I'm going to draw the compound design of AB plus CD. So what I'm going to do is, so I'm going to consider Y bar as AB plus CD bar. So I'm going to design a compound gate here and then add an inverter. All right. So the compound gate for this AB plus CD, the whole bar, I know that this AB will be in NMOS, it will be in series. So I have now A and I have now B, and this will be my output signal, and I will have 2 legs C and D forming the transistors C and D on the NMOS side. So this represents AB plus CD on the NMOS side, and on the PMOS side, its conduction complement will come into the picture. So the conduction complement represents if in the NMOS side or in the pull down side, if I have 2 of the transistors in series, that will become parallel in the pull-up side or in the PMOS side. So I'm going to draw 2 parallel transistors, connect it together, and then similarly one more parallel transistors. right? So this becomes my AB and this becomes my CD. And then this will get connected to the output and this will get connected to the VDD. So this is my circuit now. Let's size this gates or the transistor width so that we should be able to evaluate what should be the logical effort and then the parasitics. Because what we really want is this particular block of AB plus CD, which will give me the output of AB plus CD bar, should go to the inverter, making it the output as AB plus CD. And we will take the similar dimension. So the input gate size is 20 and then the output we should have it as 100C, so that we can compare between this particular technique of the compound gate design with respect to the multi-stage designs. Although this is a multi-stage design, we have one stage here and then the second stage here, but still most of the computation happens in this particular part of the stage. Because it adopts all the 4 transistors in this particular stage, so that's why we call it as more towards the compound stage design. All right, so let's try to assign the widths of this particular transistors. So we know that to compare the logical effort, we need the equal rising resistance and an equal falling resistance with respect to the inverter, so that my output current will be same. So if I want to have an resistance of R here, so I will have a size of 2 and 2. I have a size of 2 and 2. Under worst case condition, if A and B is 1, then I will get this particular leg to discharge having a rising resistance of R. And similarly, if A and B is 0 and C and D will be 1, then I will have this particular leg of C and D making the discharging path for the output capacitance. Right, so on the pull-up side, I will have a width of 4 and 4, 4 and 4 here, so that under worst case condition, either A or C or so A or C or D, or A and C or D should be 0, so that these transistors will have a successful charging path connecting the VDD to that of the output node capacitance. Or we can have another combination of B being on, so this particular transistor being on, and one of these transistors C or D should be on. So with respect to this particular sizing, I should be able to get the rising resistance as R. So once I have the width sizes, can I find out what is the logical effort for this particular inputs? All of them have the same widths. So if I consider the input capacitance for one of the transistors, one of the inputs, right, I will get the capacitance to be 6C divided by our benchmark inverters, which is having 2:1 ratio, which will give me the falling resistance as R and the rising resistance as R will give me the input capacitance as 3C, so it will give me the logical effort as 2. The parasitics again having the sizes such that we will get the same output current. So this particular sizes will ensure that I will get the same rising resistance or the falling resistance with respect to the 2:1 inverter. So if I can find out the total output node capacitance, so the total output node capacitance seen at the output nodes, or rather the overall capacitance that is seen at the output node, if you can calculate and then take that into estimating the normalized parasitic factor. So the overall output node capacitance turns out to be 2 plus 2 plus 4 plus 4. So I will get 4 plus 4, 8 plus 4, 12C. So I will have 12C divided by the 2:1 inverter will give me a total output capacitance of 3C. So the normalized parasitic will be nothing but 4. So with this particular the G and the P value here, right? So let's try to find out the delay, the minimum delay that we can extract from this particular compound gate design technique. So here is our AB plus CD with the size of 20. We know the logical effort turned out to be 2, and then the parasitic is nothing but 4. This is what we had seen in the last slide. For an inverter, we have a logical effort of 1 and then the parasitic of 1. So the total F, the path effort in this particular case will be nothing but G into H, which is nothing but the multiplication of the logical efforts and then the electrical efforts. So it turns out to be 2 into 1 multiplied by 100 divided by 20. So it turns out to be 10. And there are two stages. So if I want to find out the individual effort delay, it will be nothing but F raised to the square root of F, which will be nothing but 3.16. Right? So the square root of 10 turns out to be 3.16. And if I put 3.16, I can find out what should be this particular gate size. All right. So this particular X value turned out to be 31.6622, which is coming from GI into HI for that particular inverter, which will be nothing but 1 and then 100 by X will be my 3.16. Right. So if I can easily find out what is X. X turns out to be 31.622. That is the size of this particular inverter, giving me the best delay. And what is the best delay? What is the minimum delay here? It turns out to be nothing but the parasitic of 4, parasitic of 1, total of 5 parasitics plus twice multiplied by the individual stage efforts, which is nothing but 3.16. So the total value or the best delay turns out to be 11.32. And if I go back to our previous design, which was there in the slide number 2, I should be able to confirm that this particular cascaded multi-stage designs gave us the delay of 9.96. And if I go back to my present slide, this particular compound gate design gives me 11.32. So the delay using the multi-stage design is kind of preferred if I'm considering the delay as one of the parameters, right? Although both of them giving the same output. So let's also try to evaluate what is the overall area or the footprint of this particular design. So I now have the sizes. So what I've done is once we have evaluated what is the X value, right, from the previous slide, we have evaluated what is X, so which is 31.622. So 2:1 inverter will create 3 parts of 31.622, and then 2 parts of 3 parts will go to the PMOS side, and then 1 part will go to the NMOS side. All right, and then if I have an input capacitance of 20C or a gate size of 20 here for the AB plus CD the whole bar, so we know that for the individual input 6 parts has to be created, and then 4 parts of the 20 should go to the PMOS side, and then 2 parts of the 20 the 6 parts should go to the NMOS side. So for the 20C will make 6 parts, and then 4 parts will go to the PMOS side, and then the remaining 2 parts will go to the NMOS side, right? So this particular thing will 13.33 is going towards the PMOS side, and then the remaining 2 parts will go to the NMOS side. So that's why we get a size of 13.33 and 6.66. Right, so with this sizes, the widths of the transistors on both the stages, the first stage we have the compound gate, and the second stage we have the inverter. The total width of the NMOS will be nothing but 10.54, plus we have on the NMOS side 6.66 multiplied by 4, so it will give me 37.18. On the PMOS side, we will have 21.08 plus 13.33 multiplied by 4, 74.4. So if I consider our previous case where it was 84 something on both PMOS and NMOS, this particular size has drastically reduced. 37.18 on the NMOS side it's a drastic reduction in the total width of the NMOS side. PMOS side also, it has reduced by almost the size of 10. So compound gate design offers actually less width, which will indirectly help in having a less area. So having a very compact footprint of the design. But of course, we will have to compromise in the delay when compared to that of the multi-stage design. Right. So this is one such perspective that has been given. The output remaining the same, the input gate sizes are the same, the output load capacitance being the same, but still we have two designs giving one giving a better delay results, the another one giving a better area results. right? So hope you have understood this. So moving on, the asymmetric gates, and there's an empty slide. That means that I have to draw a diagram here. So let's start with an 2-input NAND gate. So what we had seen is a 2-input NAND gate with the same sizes for both the inputs. So I'm going to draw a 2-input NAND gate. This is VDD, and then the other one is ground. And here we have the PMOS transistors and then the NMOS transistors. The sizes which we had used was 2 and 2, and then here also 2 and 2. And if I consider this as A and A and then this as B and B, so we know that the input capacitance of A and B remains the same. The input capacitance for A is 4, the input capacitance of B is also 4. Now let's take another variant of this 2-input NAND gate. So I'm going to write it as 2-input NAND, and I'm going to have the same design in the form of the transistor level. So it is nothing but a 2-input NAND gate. So it will have the same design. And I'm going to say that on the PMOS side, I'm not going to change the sizes. All right. But on the NMOS side, I'm going to change the size. And I'm going to say that this is 4 by 3. All right. But I want this falling resistance to be the same as that of the falling resistance of the 2:1 inverter. Right. 4 by 3 is likely to give me a resistance of R by 4 by 3, which will be nothing but 3 by 4R. Okay. And if I choose a width of 4 here, this one will give me a switching resistance of R by 4. The total of this switching resistance, the sum of this switching resistance and this switching resistance will give me the switching resistance of R, and which is what we want when we want to compare the logical efforts or the parasitics, or when we want to estimate the logical effort or the parasitics with respect to 2:1 inverter. Right. So what we have done here is I have changed the widths of the NMOS transistors for the 2-input NAND gate. Up till now, we had seen the same sizes. Now we have changed it into a different widths, right? But giving the same falling resistance, right? Here also the falling resistance was R. Here also the falling resistance is R, right? So, but the widths of the transistors now are not symmetric anymore. So that means the input capacitance seen by the input A and the input B are asymmetric. That means they are different. So the input capacitance seen by the A input will be nothing but 2 plus 4 by 3. Right? So it will be nothing but 2 plus 4 by 3. The input capacitance seen by the B input, which will be nothing but 2 plus 4, which will be nothing but 6C. So hope this is clear. Moving on. Now, why do we do this? Having an asymmetric gates, right? So input capacitance seen by the inputs are different. So that's what it means. So on one side, we have a larger input capacitance for this particular transistor, and then a smaller capacitance for this particular transistor, right? And generally, it has been, generally the why it is used is, if we have A and B and one is a data signal, so this being a data signal and another one is a control signal. So let's say that the B is a control signal. So the control signal is of low frequency, in the sense it is operated not every time. So it is operated at a low frequency. So once in a while it will come into the picture, it will be enabled. And that is when the B is going to get operated. The B is going to get a signal of 1 rarely or at a low frequency. All right. So in that sense, so now I will have a capacitance associated with this 4C. So because it occurs very rarely, this 4C, when the output gets, when the output here has to fall down from 1 to 0, right? Even this particular capacitance will discharge. All right. So this capacitance being more, so 4C is actually derived from the width of 4 here. And because I have increased this width, this capacitance also increases, and then this particular capacitance has to discharge. Right. So this particular very rarely occurring signal, whenever it happens, this 4C capacitance has to discharge. All right. And this particular data signal, so this particular data signal is a high frequency signal or occurs more frequently. This particular signals, incorporates, so the transistor here is of the size 4/3, so that means that the output capacitance here, right, is nothing but it incorporates 4/3 capacitance, right? Of course, this 4/3 will get added up with this particular 2 capacitance and then 2 capacitance. But what I'm saying is, if this, if I can change this particular width here, it is going to accommodate to the output node a lower capacitance. So my output node capacitance is likely to decrease, which will, lessen the parasitics, right? And also the logical effort of this particular data signal, which is the A signal connected to this particular transistor, that is also going to get reduced, right? And this 4C capacitance also, although 4C is likely to take more amount of time to discharge, but because it's a rare signal, it's a low frequency signal, that is perfectly fine when compared to a mostly occurred signal, right? And this particular whenever we do this size increase in the size of the transistor, so this particular transistor input is also made available, is also connected to the early arriving signal. And the reason is, if suppose I have two signals A and B, if the B arrives early, then it becomes, the 4C capacitance here can easily discharge, right? If B is 1, then the 4C can start discharging. It doesn't have to wait for the A signal to arrive, right? So in that sense, if among the signals, if we have calibrated or characterized in such a way that we know that among these two signals, B is always arriving early, then I can easily increase the width of this transistor during my designing stage, so that even if I have a very high capacitance, it will get discharged early because B is arriving early. At the same time, if I increase the size of the B transistor here, I can compensate with having a lower size here, so that we will get an equal falling resistance of R, and a lower size on this particular transistor will help in not only help in decreasing the parasitics, but also the logical effort for the transistor A. All right. So let me try to find out what should be the logical effort of the transistor A, which is nothing but 2 here plus 4/3 divided by 3, because I'm having a 2:1 benchmark inverter, which is seeing the same current, output current, because of the same falling resistance or the same rising resistance. So the logical effort of A is nothing but 2 plus 4/3 divided by 3, 10/9, which is actually less than 4/3 of the 2-input NAND gate, which we had seen earlier. So 10/9 is actually less than 1.33. What about the parasitic? The parasitic here, because 4/3 is a less size, so a less capacitance get incorporated into the output node. So we now have 2 plus 4/3, which is 16/9, which is kind of less than that of the value 2. So both my parasitics and then the logical effort, according to the linear delay model, has decreased, right? And where we have compensated into the other transistor, which is B. And naturally, the other the logical effort of the B transistor is going to increase, because it will be 4 plus 2 divided by 3. It will be 2, and then 2 is greater than the 4/3 for the 2-input NAND gate. But this is okay, because this is well accepted, because this B transistor is either, it's a rarely occurring signal, so it is a low frequency signal. So only at that rare events we will use this particular logical effort to find out that particular delay. Although in that rare event we will have a larger delay because of this B transistor path. But overall, most frequently the A signal is our data signal. So this particular path is going to have a less delay because of the less logical effort and less parasitics. All right. Hope this is clear. What if I make it more? So let's, instead of 4/3 and 4 here, if I make it 100/99, and 100 here. So I have a huge width here on the B transistor, and A is nothing but 100 by 99. Naturally, the logical effort of A will be nothing but 2 plus 100 by 99 divided by 3. Turns out to be very, very close to 1, which is nothing but that of the logical effort of the inverter. Right? Very, very less than 1.33 or the 4 by 3. B, if it is 100, it's going to drastically increase. 100 plus 2 divided by 3, 102 by 3, which is very, very higher than that of 4 by 3. If it is really a low frequency, we can try accommodating this. But remember that a size of 100 is going to increase your area drastically when compared to a size of 2:2. Right? So if I consider a 2-input NAND gate with the NMOS size of 2 and the PMOS size of 2, or NMOS size of 2 and then PMOS size of 2, we used to have, the size of 2 is very, very less compared to that of the 100. So if we really want this particular data path to be, to have a very high performance, then only we increase this particular size, right? Otherwise, we have it 2:2, or we can try to accommodating 4 by 3 here and 4 here. So this is another extreme case of improving the delay of the data signal, but compensating with only the low frequency or early arrival signal, which is connected to this particular B transistor. Right? Hope this is clear to everyone. So I'm going to stop my lecture here.